Assalamualaikum warahmatullahi wabarakatuh. Alhamdulillahilladzi hadana lihada wa ma kunna linahtadiya laula an hadanallah. Asyhadu an la ilaha illallah wa asyhadu anna Muhammadan abduhu wa rasuluh. Allahumma shalli ala Muhammad wa ala alihi wa ashabihi wa man tabi'ahu bi ihsan ila yaumiddin, amma ba'du. Hello student. Today we discuss about the external disturbance in process control. We illustrate you. We have a system here, a liquid heating tank with stir. In this system, we have one input inlet stream with flow rate is Fi and temperature of input is Ti, and the flow rate output is F and temperature input is T. We can assume here that the liquid in the tank is homogeneous because we have stir here, and the temperature in the tank, temperature liquid in the tank is equal to temperature liquid that out from this tank. And we use one coil to heat the liquid in the tank using steam. What is the objective of the system? We can see this. The objective of the system is the temperature output of the liquid from the tank, and we want the temperature to add desired value, and we call this the Tt. This is the desired value of the temperature output liquid from this tank. And similarly, maybe we have another objective. For example, we have H, the H level of liquid in this tank, the H level of liquid in this tank, at any desired value, Hg. This is the objective of this tank. We know in the system, in chemical process, is initially from start up and then running into the steady state condition. You know about this illustration. Initially the system run in startup, and by the time we're running into the steady state. We always assume a system when established running in steady state condition. When there is no external disturbance, there is no change of flow rate of Fi and Ti, there is no change of flow rate and temperature input Fi and Ti, or there is no change of flow rate of steam. So the system remain in steady state condition. In this condition, there is no control system we need. But in practical, we know that the flow rate of the input or temperature of the input maybe can change by the time. This is the function of time. So do the flow rate of steam. This is the function of time too. Maybe not all of time, but in any interval of time, the Fi and Ti or flow rate of steam may be changed. So we cannot control the Fi and Ti exactly. So we need to control the system to maintain the temperature output of the liquid at the desired value that we set in TT, and the level of liquid is at desired value which we set at HG. Would you suggestion for you? Suggestion from you about this control, to control the system. How we can keep this temperature into desired value? How we can control this? To control the system, firstly, we have to measure temperature of the liquid using any temperature measure equipment. We can use the thermometer or thermocouple. From this measurement, from this equipment, we get the temperature of the liquid, the value of temperature of the liquid, and we compare this value to desired temperature that we set in the controller. We can compare this. This is the plus, this is the minus, and we get the error. The formula of error is temperature desired minus temperature, vice versa, okay, no problem, or T minus TD. When you sign, this is negative and this is positive. Okay, we focus in the first definition, the TT minus T as error formula. From this, the error value will send to controller, to any controller, and this controller will translate the value into the action element. The action element, what is the element? To act, to maintain the flow rate of steam. It's control valve, the control valve to maintain the level of flow rate of the steam. So the temperature of liquid can keep to desired value. That is the control system that we imply in this system, to maintain the temperature into desired temperature. When there is disturbance in input variable, in this case for Fi and Ti, or Ti, not NTI. We can see this formula. The error is Tt minus T. In any condition, we got the error is greater than 0. That means the Tt greater than T. When Tt greater than T, what will we do for this system? When Tt greater than T, we need more steam. We need more steam. So when we get the error greater than 0, that means the TT greater than T, we need more steam. So the controller will translate the error to send the signal into this controller to open up the control valve, so more flow rate of steam input in the system. In contrary, when we get the error less than 0, what does it mean? The TT lower than T. What will we do when the TT lower than T? So the T upper our target. And what will we do? We have to reduce the flow rate of steam. So the controller will reduce the steam. This is the mechanism, the control system, to maintain and to keep the temperature into the desired value. Okay? In any condition, when Fi increase, what happened to the system? When Fi increase, maybe the T will decrease. So to keep the T into the TT level, we have increased the FST, the action controller. So this is the mechanism of the controller action. This is the mechanism of the controller action. That is the illustration how the external disturbance disturb our system and disturb the output of the system. For example, in this system is the temperature of liquid. The temperature of liquid that we set to the desired temperature, and when the disturb in input variable, we need the controller to maintain the temperature of the system into desired value that we want. So this is illustration how the external disturbance disturb our system and how the controller to action to maintain our variable, for example, temperature output of the liquid, to maintain the system into the steady state condition. And then we're talking the second issue for the stability of the process. Secondly, we discuss about the stability of the process. Firstly, we draw a plot. This is the X and this is the time. The X can be maybe temperature or concentration or flow rate. In this situation, from initial into the time t0, this is the condition steady state system in steady state, and then this is the steady state value. At the t0, the system is disturbed. We note this, X is disturbed. at t equal to t node. As a result, the x will be changed in value, but by the time into the steady state value, in this situation, we call this the x return automatically to the steady state value. For system like this, we call this the system is stable. The system is stable or self-regulating process. Why? Because when the system is disturbed by any condition, the system will going to the steady state value by itself. No control action to the system. So the system is stable, self-regulating process. So for the process like this, we no need any external intervention. No need external intervention. What does it mean by this? No need external intervention. We can say this: no control system need. Why? Because the system is stable and the x value will return automatically to the steady state value. So there is no control system we need. Okay. We have another system like this. We plot x and versus the time t. In initial value of the system, from initial, the system is steady state, and at the t node, the x is disturbed. The x is disturbed at t equal to t node, and then the system give response like this. This is the response of the system, and the value of x never return to the steady state value. How about this system? This is unstable system. We call this unstable system. Why? Because the value of x never return into steady state value by itself. So the system is unstable and need external intervention. So I can say for this system, we need control system, or we need the controller. Exactly need for the system. But how about the stable system like this? This system is need the system need the controller. Even this value of x will going to steady state value by itself, but you can see this, the period of time to back to the steady state value is at the t, or we want to the steady state value, or the period of time is shorter the period of time. When we want to the shortest of the period of time, not in this here, but in this condition, this here. So we need the controller to make the period of time is shorter than this period in regulating, in self-regulating by the system. So the stable of the process that's stable or self-regulating process also need controller. What for? To reduce the period of time to return in the steady state value. So to make the process faster to steady state value like this. So we need the controller too for the system. The third issue is performance of the process. Okay. For optimize the performance of the process, we have the main objective here. Main objective. Firstly, the main objective is safety. Okay, safety. Always safety. And the secondly, the main objective is product specification. Product specification. To illustrate this, I give you one example, the CSTR, continuous start reactor. In one reactant here, we use this is the flow rate of reactant and the product here, and this is the jacket reactor. We have the jacket here to maintain the temperature of the reaction in this reactor. The reaction in this reactor is consecutive exothermic reaction from A to B and then from B to C. You know about this reaction. This is the series reaction, and this is the exothermic reaction. So we need the jacket, we need the cooling water. We use the cooling water to maintain the temperature of the reaction in this tank. The product B is the desired product. The A is the reactant, and the B is the desired product, and the C is undesired product. This is the desired product. And C is undesired product. You can see this. Our desired product is intermediate product. What is the economic objective? In economic objective, in economic objective, how about economic objective of this system? Economic objective, our system is profit. Yeah. How about the profit? How we can maximize the profit? Profit is a function of product P, revenue of product P, and maybe the reactant A, and function of the coolant, yeah. Because this is exothermic, we need the coolant. We need the coolant here to cool the reactor. So this is the function of coolant. This is our formula to optimize the profit. Is function of product P, function of the desired product, function of the reactant, function of the coolant we use to cooling the reactor. This is the economic objective when we want to optimize here. You can see this, that we need the controller to control the temperature of the system, to design when the product P as desired product to maximize MON, and the product C is undesired product to minimum, and we use the optimum coolant to optimize to cooling the system, to cooling the reactor. Okay, that is the illustration of process control in the three issues. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.